All right, so for thermodynamics, we're just going to go over a few things real quick. Again, this is stuff we should already know from general chemistry, but let's remind ourselves. So, thermodynamics describes energy as well as equilibrium. Okay, so remember this is a KEQ is equal to the concentration of the products over the reactants, and then if there's a coefficient, you put that at the like concentration of C to the power of whatever that coefficient is. And that's our equilibrium equation, right? And so we should also know that when KEQ is greater than 1, the equilibrium favors the products. Okay, that means we have more products than reactants since those are in the numerator. And then the reaction lies to the right, or the equilibrium lies to the right for that particular reaction, which is ideal, right? We want to make the products if we're trying to make things. When KEQ is less than 1, equilibrium favors the reactants, and the reaction lies to the left, or the equilibrium lies to the left. So this one's not very ideal, right? Because that means we're not doing anything. So for a reaction to be useful, we want the equilibrium to favor the products, obviously. And so that means we want KEQ to be greater than 1. And that, again, is because if we have the concentration of KEQ equal to the concentration of the products over the reactants, then if it's greater than 1, then that means the concentration of the products is greater than the concentration of the reactants. Okay. And so that leads us to the question, what determines the equilibrium position? Like, why is this even a thing? And so that is Gibbs free energy. So hopefully you guys remember this. That's delta G. And so there's a couple equations for delta G that we'll introduce. But first, let's define it. And that is the change in energy that occurs during a chemical reaction. Okay, and so delta G is equal to delta G of the products minus delta G of the reactants. Okay. All right, so a couple terms that come along with this. Exergonic, which is when it's kind of like exothermic and endothermic, right? The reaction with a negative delta G and is therefore spontaneous, meaning the reaction is spontaneous and will occur. And then endergonic is when the reaction has a positive delta G. And that means that the energy is absorbed, and so this is not going to favor the reaction moving forward necessarily. Okay, so when KEQ is greater than 1, the log of KEQ is a positive value, and that makes delta G a negative number. Okay, so that means that it's exergonic, and again, that means we want KEQ to be greater than 1, as we stated above. Okay, so that KEQ less than 1 means that the log of KEQ is going to be a negative value, and that makes delta G positive. And again, that's going to give us an endergonic reaction, which we don't want because that means the equilibrium favors the reactants. Okay. Delta G is basically going to just be equal to negative 2.303 RT log KEQ. So that's where that log comes into play and what we mean by giving us a positive or negative value for G, right? So R is a gas constant, 8.314 joules per mole Kelvin, and then temperature T is in Kelvin, of course, per usual. Simmer down now. All right, so the equilibrium favors the product when they're more stable. So remember, stability means that it's going to be lower in energy. So lower in energy is, it's kind of related to the acid-base chemistry, right? The more stable the conjugate base, then the lower in energy. So, and that's with respect to the reactants. So delta G, if we have that in the y-axis, is increasing in energy, and we have the products on the top and the reactants on the bottom. That means the products have a higher delta G, right? And that means that delta G is going to be greater than 0, and KEQ is less than 1. So that means it's going to favor the reactants. Now, if we draw the same setup, but instead of having the reactants on the bottom, we have them on the top and the products on the bottom, that means that delta G is going to be less than 0 and KEQ is going to be greater than 1. And remember, that favors the products because the KEQ equation is products over reactants, right? So more products means a greater value than 1. So what is the relationship to conformation and energy? I remember we would draw chairs and we're like, here's the chicken foot in the axial position, and then here's the chicken foot in the equatorial position, and what's the percentage of each of these compounds, right, or these conformations, and it was 100% in the equatorial position. And you're like, yeah, I agree with that for just because you told me. Well, the reason, not just because we say so, is because of Gibbs free energy and the calculations we can do with the equations. So let's say we have these two, we have a phenyl group in the axial and equatorial position. That's pretty big, right? We don't know how big that is relative to a chicken foot. But let's say we were given an energy difference of negative 12.1 kilojoules per mole for that axial to equatorial. If we plug that into delta G, we can technically compare those values or solve for KEQ, right? And so KEQ gives us a representation of products and or it gives a relationship between products and reactants. The equatorial would be the product in this case, and then that occurs at 100-to-1 ratio, or 100 times more equatorial product than or conformation than the axial position. And that's because if we have 12.1, we can determine KEQ is equal to about 100. Okay, and so that is essentially how we determine that we have either no products, no conformation in the axial position, or just some, or something like of somewhere in between, right? And so this chart right here is going to give us an idea, again, with delta G and kilojoules per mole, KEQ, and the relative amount of products A and B. Okay, so this is a cool chart. I like this because it actually gives us some idea or some perspective as to what kilojoules per mole really means in terms of energy, right? We just say like, oh, that's 18 kilojoules per mole, or that's 6, or negative 12, or whatever. Like, what does that even mean? So this gives us some perspective. So as we go down, we have an increasing amount of product going A to B. And so if you have 18, positive 18 kilojoules, that gives you 99.9% A. That's mostly A. And as you work your way down, you go 100, 10, or equal amounts. And then once you get into the negative values, you're starting to favor the products. And so you get 10 times more B, 100 times more B, and then 99.9% B, so mostly B. And so that's delta G. Kilojoules per mole. We also have another equation that relates kilojoules and moles, right? Enthalpy and entropy are some other variables. And remember, delta G is equal to delta H minus T delta S. And delta S is the entropy, and enthalpy is delta H. Also remember, delta S is typically discussed in terms of joules, while enthalpy, delta H, is discussed in kilojoules. So that means that delta S is pretty small. Those values are pretty small and can often be ignored depending on the conditions of the reaction. But what that means is delta G is approximately equal to delta H. Okay, well, you're probably like, well, cool story, bro. Why do I care? Well, it's basically just saying that delta G, even though we're talking about delta G and energy, we can discuss them in terms of delta H, and we will in the future, and that's why it's important to point that out. Okay, so let's take a look at some delta S examples. So basically, we have a carbocation combined with water, and you make an alcohol, right? And so really what this means is we've got two compounds on the left, and then we are combining them. We are doing an addition reaction, and we are making one compound. Okay, so we have more order on the right and less order on the left, or the left is more disordered. And so that means we have lower entropy on the right and higher entropy on the left. Okay, again, what does this mean? Well, it just means that the reaction isn't necessarily entropically favored, okay? And in terms of entropy, it is not ideal to go to the right, but it definitely is possible. It just depends on the other conditions of the reaction, right? And we said delta H is mainly the deciding factor anyway. So let's take a look at this problem. Well, we got an alcohol. We've seen this before, right? And so we went from an alcohol to an alkene, and we have one compound going to two. This increases the entropy, and therefore it is favored because we have two products on the right and one on the left. Okay, so these types of reactions are still, even though they're favored, they still might be difficult to drive forward. Okay, and so again, just depends on the other conditions. Okay, that's pretty much it for thermodynamics. Okay.
All right.
Bye.
So I think the Mitch Hedberg jokes were kind of a hit. So if you don't know Mitch Hedberg, here's a couple coming at you. So let's see. One of my favorites is I'll say that one for last actually. And these are rated G for guidance. So you know how the fishing shows, how they catch the fish and then they release it? They don't want to eat the fish. They just want to make it late for something. All right, here's another one. So I want to get one of those world maps and then hang it in my house and then put pins on all the locations that I've traveled to. But first, I got to travel to the top two corners of the map so it doesn't fall down. All right. Here's the last one. This is good. Oh man, if you don't like him, I'm sorry. Well, I'm probably butchering him because Mitch Hedberg, his delivery is on point. So check him out if you're okay with a few bad words. And then let's see the last one. Hey Mitch, do you want a frozen banana? No, but I want a regular banana later. So yeah. So good. All right. Peace, love, and Ocam. Bye.